I request everyone to kindly maintain silence. Sharing is good, and with digital technology, sharing is easy. Good morning to everyone present here. I am Darwin Noel from ECE department,
I Ankita Shetty from EC department.
and it's an honor for us to be here hosting this event. I would like to extend a warm welcome to all of our distinguished guests, faculty members, and fellow students who have gathered here for this event.
A hearty welcome to the expert speaker of the day, Mr. Sagar Somshekar, Senior Architect, Nokia Network, Bangalore. Mr. Sagar has 12 years of experience in wireless communication, signal processing, radio frequency, and antenna domains. He is currently working as Senior Architect at Nokia. He completed his MTech in signal processing and communication from IIT Kanpur in the year 2015. He had also delivered several technical talks and has won several awards. We welcome you, sir. Now I would like to call upon the speaker of the day, Mr. Sagar Somshekar, to continue with his session and keep the crowd interactive.
Very good morning to all. Thanks for thanks for attending and thanks for the kind introduction. So let's get started. Okay, so um, I will be talking about digital modulation techniques and detection and estimation theory. So what I will do is I will cover some of the topics related to the big picture in the beginning. Okay, then I will move on to the various modulation techniques, and then we will see why many modulation techniques are proposed in the literature. Okay, then we will touch upon estimation and theory concepts, and then I will tell about some materials. Okay, so all are active. Okay, so I will be also covering some of the basic concepts, whichever is required um, to cover the technical aspects. Okay, then I will be writing it on the presentation. So I hope that is okay, and if it is not visible, please let me know. All right. So the first thing is the big picture. Okay, so in the previous semester you guys have studied about the analog communication, right? So you have studied various modulations, so AM, FM, and PM. First, if already analog communication is present, then why do we need a digital communication? So definitely there are some disadvantages, right, with analog communication, and we are not able to scale it up to provide more and more services. So from the application point of view, it is very limited. That's why I think we are moving to digital communication. So then, what are the disadvantages? Yeah, can some of you tell what are the disadvantages you have gone through in fifth semester, right? Analog communication. Okay, next. Okay, okay, good. So, yeah, most of the answers are correct. But I want to give some different perspective that in the analog communication, what did we have? Okay. Mm, so in the analog communication, what is the input? Input itself is analog, right? So we are giving input which is analog signal, and then we had a carrier. Okay, So carrier is also analog, but it is of a very high frequency, and then we used to transmit over the air. Whatever the signal we have, input signal, which is a message signal, so we have found out many techniques, right, to process that message and the carrier, depending upon the modulation schemes like AM, FM. But when you process, what were the circuits or what were the block diagrams which you were using? Something like envelope detector or phase lock loop, right? Zero crossing detectors, mixers, translators, things like that. So these are all hardware components, and these are all okay. The moment it is a hardware component, these are all bulky, and the moment you are going to incorporate more and more hardware, it is costly also. All right. So got the point. So basically, we are processing the signal in analog, and for that we are using lots of hardware, and that will make the communication system costly, bulkier, and also and if you see many phase lock loop and things like that, they are all complex in nature, right? Complex receivers and things like that. So we wanted to eliminate these hardware component, and we want to move to the digital processing, or in the processing in the digital domain. Okay, so I think that is clear, like why we are going to digital communication, right? Now let's say we are using digital communications, we need to look at the advantages. Okay, so obviously if the noise is a lot of hardware components, if you are using, noise is too much there in the analog. But if you are processing many of the things in the digital domain, then your digital communication becomes more robust to noise. All right, then today we have lots of equipments, right? Even you have computers where it process the information in terms of bits, ones and zeros, right? So if you are also performing this communication system, if you are also performing in digital domain, then it is more compatible to many other equipments which are already there. Correct. Even we have internet, and internet process the information in terms of bits. So it will be very much useful if you are also processing in bits. And apart from that, what else? So in analog communication, you have seen only a limited modulation schemes, right? You have only AM, FM, and PM. Is there any other modulation scheme, right? But right now you are going through the digital communications. So in the modulation techniques module, you're seeing, right, there are lots of modulation schemes that are proposed. So the digital modulation, once we are processing the signal in the digital domain, it is giving us the flexibility to scale up, or it is giving the flexibility to propose more and more techniques, and we can see which one is better suitable for our practical purpose, right? Such a kind of flexibility it is providing. And even many other techniques like multiplexing, multiple access, and even in terms of encryption, it is giving more flexibility to scale up the system. Okay, and by that way, we are also able to go for much more services with the digital communications. Okay, let's say what are the services provided by analog communication. Okay, we have seen few modulation techniques, right? Okay, go ahead and answer. So what are the applications of analog communication? Are you using analog communications? Yeah. So name it which you are using. Let's say on a day-to-day basis, or in your real life. Sorry, the communication. Just speaker is only one part. Are you guys using FM radio mirchi, something like that? So that is a FM analog communication, right? So what about in TV? So in analog communication we had VSB, vestigial sideband modulation, right? So that was used in television, right? Okay, now digital communication. So let us say where you are using. Are you using? So you guys should know. You guys should know the applications very well, so that it connects, right? Whatever you are studying, you will be able to connect it very better. And also, like when you're trying to understand the concept, like if you know where it is used and if you're trying to relate to that, you will be able to get the concept very easily. So anybody thought about it and linking to the application? So where else, where are we using this digital communication? So you all have mobile phones, right? So in your right now mobile phone, we are already employing lot of digital modulation techniques. Okay. So from that perspective only, we will try to see the concepts and we will try to understand. All right. So I hope it is clear related to advantages of digital communications. Okay. So from the big picture, right? We will try to see if we are looking at the digital modulation techniques in this whole communication system. Okay. Right from your transmitter till receiver, in which part we are basically looking. So that will give the more clarity, and also we will see whatever subjects you are studying. So those subjects are linked to what kind of concepts. So we have on a very high level we have transmitters, then channel and the receiver, right? Okay. So now I will just consider the analog communication. So this part, we have already spoken. Okay, input is analog, and then we process in analog domain, and we're gonna transmit it. Okay, as I was telling, I will be covering the basic concepts as well. Some of the basic concepts and some of the some default things so you should be knowing so that it is easy to understand. First thing is that in this real world, what kind of signal would be transmitted? Okay, so in this real world, only analog signal is present. Am I right? See, right now I am talking. This is one kind of signal. Okay, so this signal is analog in nature. So in the real world, the moment it comes to outside world, first of all, it is analog signal. Then it is a real signal. Okay, not the complex signal. All right. So we will have these two things in our hand. Then, in case of analog communication, uh, okay. Now coming to digital communications system point of view. Okay. So since let's take mobile only. Okay. So let's say I call to some person and I'm talking. So analog signal is coming out, and then your first of all your mobile will catch this analog signal. Okay. And then there are some transducers and we have many. Initially we will have some processing in the analog domain. Okay, so that's what I have written over here. So the input is analog signal only in the I mean in the very big picture, and then initially we will process in the analog domain. So here what do we process? Okay, like transducer we are converting into the some electrical signal, and after that here you will use analog to digital converter. Okay, so then you will get bits. So to this digital processing block you will get bits. So here I'm telling there is an analog to digital converter. So what do we need? So we need the concepts of sampling, quantization, and things like that, right? So that is studied in your module 1. Am I right? Okay. So now we got bits, and there are many operations which we can do using those bits, depending upon the technology which we are using. So we will process those things in the bits. Okay. But here one catch is that, see, I was telling, when we are doing analog processing, we need hardware, right? But here we are having bits. Then what do we need to process these bits? What do we need? So let's say, let's talk about your computer only. So it is processing in the bits format, right? Ultimately, how is it processing, or how the bits are processed? Finally, in the CPU, if you open up and see, like, you will finally have, you know, arithmetic logic units, right? ALUs you will have that will perform addition, subtraction, multiplication, and all these things. So these ALUs are actually, finally, at the end of the day, it is hardware only. But those are all very less costly compared to the kind of complex hardwares which we are using in the analog processing. Okay, point number one. Then these ALUs, right? Um, like, from which subject you can connect to those ALUs. Now I said it's an hardware. What kind of hardware it is? So it's a VLSI, right? So in the VLSI subject, you have seen CMOS transistors and things like that. You have seen CMOS inverters, adders, and things like that, right? So those things are used basically at that ALUs. Okay, and what do we have? Like, we have CMOS, nanometer technology, right? 14 nanometer, like, even we have like 7 nanometer, things like that. So what does it do? It is going to bring that hardware, or that basically processor or chip, to a very very small in size. That's why nowadays you are seeing your mobile phones and all very compact, right? Even your television, even your computers, you're seeing more compact, right? Even the laptop. So this is how we gonna I mean, this is how we gonna process these bits. But to perform this, to perform the operations in ALU, basically we will write, these things in C language. We will use basically software. So we have to code the algorithms in C language. So then, finally, that will be performed in ALU. All right. Then finally, I'm at the end. I'm telling the still we need analog processing. Okay, why do we need analog processing? Just now I was telling about the default things, or some basic concept, that is, to the outside world. If I'm going to transmit, I have to transmit the analog signal, and it should be real, right? So we have bits, but we have to convert back these bits after processing to, digital to analog converter, and then we have to process it analog, in the analog domain, and we need to transmit. So is this clear? Okay, so this is, so I am coming from the big picture. Okay, I started with very broad overall communication system. In that, I just narrowed down to TX only, and I was comparing in the transmitter path how is analog and how is digital. And then now I am still narrowing down to only these block. Okay, this one, digital processing block. So to this block, what is the input? So we saw bits, right? 0 1, these are the bits. So output will be, again, it will be a discrete signal, or let's say, for example, it is a complex quantity. I will come to this point how this is a complex quantity or things like that. Or still, since you guys have already studied analog communication, what I would say, usually we will try to modify the amplitude or phase of the carrier, right? So these bits finally should map to either amplitude or the phase. So that's why I've written Re to the power of J5. So in the complex form, A plus JB. Okay, so what we will do here, we will try to still narrow down to what we are going to talk. Okay, so right now we are in the digital processing point, right? So here I think now we should talk about a digital communication system. Okay, so tell me the blocks which you know. Okay, let's say the input is bits. I'm talking about a digital communication block. Let's say what would be the first block. How many modules are completed right now? All five completed? Then three modules completed. Three modules completed, is it? How many completed? Only one. Two modules. Okay. Let's say one or two. So this is the third module which we are talking right now, right? So in the first module, we already saw first module would come in this point, analog to digital converter, or let's say digital to analog converter, sampling, quantization, and things like that. I think there are much more concepts in the module one, I think. Okay, but on a very high level, digital communication blocks. Okay, let's say, so the moment we have these bits, first block would be source encoding. Okay, now you are able to relate. So then we have channel encoding. So like that, we have many blocks. So here, as I was telling, this we are processing in the bits, right? We can have some encryption block as well. Okay, then let's say some kind of multiplexing block. These are all optional, okay, but I've written to say that yeah, we have the flexibility to have much more techniques, right? So let's say these are optional, but one thing is mandatory at the end, that is a modulation block. Finally, these bits should be modulated. Okay, then uh, I was telling there is an analog processing. So this I will come to this as well. I think we need to touch upon this because we need to understand the concept in a better way. So now you got it. Like we were looking only digital signal processing block. In that, right now we are going to talk about only this modulation. Okay, and some aspects in this area. Okay, now tell me these blocks in which subject you are studying. So, in which semester you have information theory? Fifth semester. There you already studied, right? Channel encoding, encoders, Hoffman coding, things like that, right? So that is over, right? So now we will talk about only this modulation. And since to this modulation block, the input is again bits. Okay. So then at the output, we know what are we going to get, which is a complex quantity, or which is amplitude or phase. So I hope this is clear, like which block we are going to talk, right? So now we are talking about modulation, but first and foremost thing is I want to actually clear the difference between baseband modulation and passband modulation. Okay, first we will, so okay, let me say, in this modulation block, right? So here we are taking the bits and we are modulating it. So here we are performing the baseband, but we also need one more modulation, that is passband. Okay, that we will do here in the analog processing after the digital baseband modulation. Okay, so first I will talk about the digital baseband modulation. let's say we have 10110 as the input bits. So what would be the easiest way? Let's say finally we need analog, right? You can map 1 to, let's say, plus 5 volts and 0 to minus 5 volts. Let's say you're not going to transmit for a longer distance. Let's say you're using some kind of cable, okay, from one point to another point, and this is for a shorter distance. Then you can transmit this directly, this baseband signal via that cable. Okay, then there will be some distortion, but you will be able to receive the signal. But for a longer distance you will not be able to do it. So what is the approach that we need to take? What is the approach? So the approach is, in analog communication, you have already seen, right, that we need to perform up conversion. That is like, to the message signal, you are going to use a high frequency carrier, and you are going to transmit over the air. This also you can transmit over the air, but what is the problem? Within a very short distance, this will get attenuated. You will not be able to achieve the communication effectively. So this information should be carried with some high frequency carrier, okay, and that high frequency carrier is transmitted over the air. But another disadvantage with this kind of pulse is that this is low frequency, right? So you already might be knowing the disadvantage, that if you're using the low frequency signal, then you need a very huge antenna to transmit, right? So the moment we are going for high frequency, we need very small compact antennas. So even your mobile phone, your antenna size will be of just centimeters, like that, right? So that's why we need high frequency carrier. But okay, before going to that up conversion or high frequency modulation, first I want to talk about this pulse, right? So we are representing this plus one, we are transmitting using this rectangular pulse, let's say. Okay. So now here again comes the basic and fundamental concept. So there are few basic and fundamental concepts which should be there in your fingertips. Okay, then your communication becomes very easy. That is one point. The another one is like, let's say, I don't know, I think in the next semester you will attend placements. I think even cap gemini, I think it will come, right, related to wireless communications. They will hire for wireless communication domain. So for that, um, you need all these basic concepts. So it would be asked in the interview. And even let's say if you are going for writing gate examination or IES examination, so first of all you should be very good at these basic concepts. Then you will be able to understand the complex concepts very well, or you will be able to connect it better. So these basic concepts, some of the questions have already come in the gate examination. So but these are all very much important for communication. So we cannot transmit one particular bit for a longer duration, right? There should be a defined duration over which you are going to transmit the bit. Let's say that bit duration is TB, and we are going to transmit as a pulse. Then the relation between bit rate and bit duration is given by this, right? Now why can't we actually transmit the bit for a longer duration or something like that? Or let us say, you're transmitting some signal. Then what is the one of the important parameter that you should look for in a communication system? That is bandwidth. This is a very key parameter, right? So how do we know the bandwidth? Let's say, how to know what is the bandwidth of the signal. So how do we know? Like, basically we need to perform the Fourier transform. This is again your signals and systems, right? If you perform the Fourier transform, it will give the spectrum, okay, at what frequencies. So this is the frequency, right? At what frequency, uh, whether signal is present or not. What is the amplitude of the signal? How the signal looks. So basically I have taken the Fourier transform of the pulse. This should be there in your fingertips, that for a pulse in the frequency domain it is a sync signal. Okay, so these x-axis values you should be very much clear. Okay, so the moment I take the Fourier transform and in the frequency domain, this is how it looks like. Then if I talk about the bandwidth of this signal, then it is the difference between these two, 2 by TB, so which is actually 2 into bit rate. Okay, so even I mean in a normal in the analog communication we say, okay, this point is the message signal bandwidth is, we will say FM, right? Then this will become minus FM, just the notation, but this FM is actually equal to 1 by TB here in this case, so it is like 2 times FM. But are you able to observe something over here? See, I am claiming that the bandwidth is this much, okay, but what is happening, there is a signal outside this bandwidth as well, but is it intended to transmit like that? No, that is not, that should not be done. Okay, let's say you might be hearing about the geo, right, recent 5G auction. So what are they going to get? Let's say geo auctioned the bandwidth spectrum, 5G spectrum. Basically they are going to say, okay, in this particular frequency this much bandwidth I want to use. Okay, for that they are going to pay how much, like they have auctioned for 88,000 crores, right, which is around 8 which is around 11 billion dollars. Now, when they say we need only this much bandwidth, they are not supposed to transmit any signal outside that bandwidth. So, if they try to transmit, then they are going to interfere with some other vendors or some other some other operators like Airtel or something like that. They should not do that one. Or let's say, hey, my communication system is such a way, I am taking some extra bandwidth, let me go for auction. But in this case what happens, it's very costly, right? Already we are seeing 88,000 crores. So if they go for much higher bandwidth, then it will be again costly for them. So they have to design the system very efficiently. So basically whatever is transmitted over here, okay, so whatever is present after this, all these things should not be done. Got it? So then that's where this concept of a match filter or this a different way of designing this pulse would come into picture. Okay, I will come to that after some time. But on a high level, I think you got the clarity, right? This is the baseband transmission, baseband modulation on a very simplistic way we had seen. Now coming to the passband modulation. See, passband modulation, we had this pulse. I was telling that we cannot transmit this pulse as it is. So we need some carrier. So this is the carrier of frequency FC. You multiply both of them. Okay. So then you get something like this, right? So then you are going to transmit this over the air. So what is going to happen to the spectrum? See, we are telling this is a base band, right? Just remember, base means actually the signal message signal is around DC frequency, f is equal to 0. Okay, now the signal is around the DC frequency, but you have to move to some other high frequency. Okay, so that's where this subconversion is done. The moment we use this this carrier, then if you see the spectrum, it is moved to FC and minus FC. Got it? So how this is again shifted, like in the upconversion, what are we doing in the analog communication? You have seen, right? How are we going to represent this? This is like AC cos omega ct, correct? Correct. This is in the time domain. So my input signal is just a pulse. Okay, that let's say this is just plus one for now. Now this plus one into AC cos omega ct. Okay, this is pulse of duration. This is plus 1 means this is pulse of duration TB. Now this is also in time domain, this is also in time domain. Okay, this is how the signal looks like in time domain. But we want to go for, let's say, we want to see in the frequency domain, right? To this signal I had taken Fourier transform here, but I just want to explain with the basic concept, or your with your signals and systems. So how can we write a cos omega ct? So e to the power of j omega ct plus e to the power of minus j omega ct by 2, right? Okay, so this pulse into, you're multiplying something in the exponential. So here I want to actually touch upon the very basic concept related to signals and systems, which you should know. That is, if you want to shift your frequency, in the time domain, you have to multiply by exponent, right? This is the Fourier transform property you guys might have studied in signals and system, right? So let's say you have x of t e to the power of j omega ct, then you take Fourier transform, then your signal would be x of f minus fc, right? So to shift in frequency domain, you have to multiply by the exponent in the time domain. So that's where, this cos omega ct I have, if we actually split it like that, and this is one shift to the positive side, this is other shift to the negative side. That's how our spectrum, which was there in the baseband, okay, in the previous, this baseband, now it is moved to, one is at fc, another one is at minus fc. I think you got it with respect to up conversion, right? Clear? So up conversion, we are going to use AC cos omega ct. Even you are used in analog communication, I'm not telling anything extra here, right? Okay, so now we will get into the various modulation formats. So till this point, you guys have any doubts? Okay, let's move on to this ASK. So similar to AM, see, now we saw the very basic digital, digital baseband, right? So let's say I have 10110, I need to transmit. Plus 1 means you transmit this carrier cos omega ct. Okay, so basically, how can I write this? So 10110. Okay, now whenever there is a 1, you transmit the carrier. Okay, then you don't transmit anything, then transmit the carrier, then don't transmit anything, right? 0, nothing. So what is the problem? Like when this kind of modulation scheme is there, again you need to question yourself. Let's say you're in the future, you're going to apply for MTech or PhD, or let's say you want to get some patents, or you want to find out some different modulation techniques. The one of the approaches is, given the modulation scheme, what is the advantage it is bringing, what is the disadvantage it is bringing. That is very much important. So let us look into those aspects here. So here, the one of the things is that the amplitude or envelope is not constant. See, right here you have very good envelope. Here you don't have anything only, right? So but what is the problem? See, right now you are proposing this, let's say, in the digital signal processing block, but you need to see it from the overall system point of view. Okay, overall system point of view means, let us get back to our let us get back to this one. Okay, so we are proposing at this point modulation, right? So what are the effects that it is going to produce in the further blocks where you are going to process in the analog domain? Okay, that is one point. Then another one is, this is just the transmitter side, right? And then you will have a receiver as well. So you need to see how well you can design your receiver as well to recover the signal. So you need to consider all those things. So in this case, what is happening is, while we are after doing this up conversion, right? So here we did the up conversion. What are the uh, further blocks we have, then we have something called power amplifiers, and then we will have antenna. So basically in the up conversion, when you're using carrier, we need a local oscillator as well, correct? So basically this is a local oscillator, AC cos omega ct. This even you had seen in our analog communication. So here the input signal, we had this pulse, right? So this is the mixer or multiplier, right? So we need to see what is the effect, since the amplitude is envelope is not constant, it has got I mean your amplifier's design becomes complex. Okay, so you will also have some kind of linearity problems, or you might have to design your amplifiers such a way that you need a you need more costly amplifiers, because you need to take care of the variations in the signal, right? So at one point in time it is very low, and other point it's very high. So your amplifier has to take care of such variations. That's why it becomes costly to design these amplifiers. What if you have very constant envelope? Then it becomes easy, because you are not going to take care of much variations, and your Q point design will become much easier, and you might, and you will not easily drive your amplifier into saturation. Okay, so now I mean that is one of the reasons why we are going to the other modulation schemes. Okay, so now what else we can look in ASK. So another point is that we'll just look into constellation. See here, we are performing AC cos omega ct, right? There is only one basis function. I will not go to the basis function details and all, but okay, we can say there is only one basis function, let's say phi 1 of t. So you can have only one dimension, that is phi 1 of t. Let's say this is second dimension, x and y two dimension, right? So this dimension I am not considering anything. So at one point in time you're here, okay, one point. The another point you are going to transmit some signal here, let's say a square root of eb. So this is the distance between these 2 points. For bit 1, this is the one which you are transmitting. For bit 0, this is the one you are going to transmit. So this is like, you can say constellation point, or you can say how you are going to map your bits using this basis function. Okay, I mean why I wanted to talk about this is, from here we will talk about the probability of error also, because that is another key parameter which we need to look. Okay, you're transmitting things, okay, using some modulation schemes, and then finally finally let's say uh, there are a lot of there are a lot of errors in the receiver. Okay, whatever you wanted to convey you are not able to convey, let's say, then what is the use of communication? First of all, communication itself is not happening, right? So the main goal of the communication itself is lost. So one of the key parameters that we should look is the probability of error. So I just want to talk about the I will just proceed with the general equation. Okay, so the generic equation of probability of error uh, is d by 2 sigma. Okay, sigma is your power spectral density of noise. Okay, this is a q function of d by 2 sigma. Okay, for now you just uh, think it is a function of some um, some parameter, but we'll try to understand the basic concept here. Okay, we'll not go through what is this q function, why this equation is coming and things like that. So but we'll try to understand this, right? This is power spectral density of noise, and we'll try to understand this distance. What is this distance? So this distance is actually distance between your 2 points in the constellation. So Okay, others are not focusing, so let them go. Yeah. Okay. Okay. All right. So this D is nothing but in your constellation. This is the distance between the 2 points which you are going to transmit. Okay. So in the ASK we had seen these are the 2 points. So the distance between them, how can we represent? We have EB here, right? So the distance is given here is square root of EB. So just we'll try to remember this. Okay, we will see what happens in the other schemes, and we'll see what is the problem with the ASK. So, but okay, I want to just talk about one more. I mean, basic equation. We should be clear. See, we transmitted AC cos omega ct, right? When it is plus one, right? But how are we saying this EB? So let's say this is the energy of the bit. How can we write? Sorry, uh, power of the bit into time, right? Power into time, energy is nothing but, so power of the bit into what is the duration, which is TB. Okay, we had that pulse of size duration TB. Now when we have this, what is the power? So these are the again basic things we should know how to calculate the power is actually, if you calculate, it will come to AC square by 2. Okay, you have to apply the your signals and system equation, you will get it. So now if you apply over here, you will get a AC square by 2 into TB into this is EB. So basically we need to catch this AC, right? So how can I write my AC? So that is square root of EB into 2 times divided by TB. Okay. Now what I am just telling is to transmit this plus 1 with energy square root of EB. So that is present over here. So now how I can write this one? Square root of EB into square root of 2 by TB into cos omega ct. Okay. So plus 1 means I will transmit EB. Okay, square root of EB. And then this will form the my basis equation phi 1 of t, which I was telling, right? Basis equation. So basically anyway this is a I carrier component. So that's how we got this EB in this constellation point. Okay, so let me write that again, this constellation point. So one point is here, another point is here. So for plus 1, this is square root of EB. For anyway 0, we are not transmitting anything, it's 0. Okay, so any doubts here? So similarly, let's go for PPSK. Okay, so in the PSK, you're able to see. Okay, so in the PSK, I mean in the analog communication, we had this equation, right? AC cos omega ct plus some based on the message, you are going to change the phase of the signal. But here for bit 0, sorry, bit 1, you say I will give directly 0, and for bit 0 I will give 180-degree phase shift, right? So I had already shown how to calculate the basis for bit 1. This is how it looks like. For bit 0, if you place 180 cos something plus 180 is a minus of that, so you got this one as well, right? Now okay, so but still if you see here, we have this cos omega ct, there is only one basis function. Okay, that basis function just now we had derived. Okay, that is over here, and that is for a duration of TB. So based on this, can we write the decision boundaries, or can we write the constellation points? Yeah, if you see here, there is a EB. Okay, but there is a minus sign. So for bit 0, this is bit 0, there is a minus square root of eb. For bit 1, square minus square root of eb. For bit 1, square root of eb we are going to transmit. Okay, there is only one dimension, phi 1 of t. All right. So now what is my distance between 2 points? 2 into square root of eb, right? What was the case? What was the distance in ask? Just eb, right? Now we were telling that we need a probability of error, so which is q into d by 2 sigma. Okay, so one thing you just remember for now, that this q function is there, right? This function is such a way that if this quantity is higher, then this is less. Okay, so in case of ask we had square root of eb, but in psk we have square root of 2 times eb. Which is greater? psk1 is greater. So if I put here this is greater, means your q function is less, which means that your probability of error is less. Now can you see that your psk system actually probability of error is less? Okay, so ask probability of error is more. That is also one of the reasons. Okay, if ask is not so clicked very well. And also we had this that constant envelope problem. But in psk, how about psk? So I didn't write those. So for +1 you will transmit like this. Let's say next is 0, then you need to have 180-degree phase shift, so you will transmit something like this, right? But envelope is constant. We achieved the constant envelope, that is fine. But we introduced one more problem, that is a phase discontinuity here. Again, phase discontinuity is a problem to the amplifier. That is also going to create a lot of non-linearities. That is not much encouraged. Okay, so this is also not a great solution. Now we have to find out some other solution. So what could be the next solution? Yeah, what could be the next solution? So we are also talking about this bandwidth, right? Okay, so we are also talking about bandwidth. Let me go back to that. So we are talking about bandwidth of ask, right? So I mean, we had already seen something like this, that +1 a pulse is transmitted, and with a high carrier my Fourier transform of the signal looks like this. Now in case of uh, you know now in case of, okay, based on that, what is my bandwidth is equal to, we had seen this particular side lobe level, right? So it was 1 by tb and minus 1 by tb. We had seen 2 by tb, which is actually 2 times the bit rate. Now let us see in psk. So in psk, how does my, this is one for +1, but what about for -1? Same thing, but in the negative direction. Okay, because we had only one basis function, and if you do perform the shift up conversion and take the Fourier transform, you will get something like this. Anyway, these two are overlapping. So again here bandwidth is 2 rb. Is this clear that bandwidth wise ask fsk similar, but probability of error psk is better. Ask had envelope problem, psk didn't had. But psk introduced one more problem, that is phase discontinuity. Okay, so what should be the next scheme? Can someone tell? Yeah, based on your analog communication, what all schemes you have studied? Okay, all right. So next one is FSK. This is similar to FM, right? So what are we going to do here? Like whenever there is a bit 1, okay. So equations are a little bit maybe confusing for now at this point. So simply I will try to explain in a simplistic way. Bit 1, I will transmit the frequency F1. That frequency is greater than your FC. Means FC plus some, let's say I will use delta F. Alright. Okay. So now bit 0, I will use another frequency F2 such that it is less than FC. Basically, this is high frequency, this is low frequency. Whenever there is a 1, I will transmit high frequency. Whenever there is a low, I will transmit low frequency. So what is the problem with this then? So here, if you see clearly, you need two different kind of frequencies. So you have to have two basis function. Okay. So I will not go through those equations, but directly, since we need two basis function, okay, and if we perform those equations, we will see the constellation block something like this. Here, let's say on the first basis function, we are going to transmit EB, and on first basis function EB, and this is a constellation point, okay. But on the second basis function, this is a two dimension, right? So you are going to transmit another point which is square root of EB, but on the second basis function. Now this is your constellation point. We had seen the constellation point even for ASK, PSK, right? Now what is the distance between the 2 points, which is square root of 2 EB. Okay. Okay. So now let us compare ASK, PSK, and FSK. Here square root of EB. Here 2 times square root of EB. Here 2 root square root of EB. Right. So this is greater. So probability of error is less. This is greater than this, but not greater than this. So probability of error is okay. This is probability of error. Now, sorry. Let's say this probability of error is very high. So PSK is far better. FSK is in between, and ASK is outperforming. But what is the problem? Like if I go back and draw my uh, power spectral density or the spectrum, right, for this particular thing, how does it look like? So one is at F1 you will have this sink, right? So now at F2, because this F1 is higher frequency, F2 is lower frequency, so I am writing it here. So F2 also you add another frequency. Now how do you consider the bandwidth? How do you consider? So this edge and this edge, right? So this edge is 1 by, yeah, F1 plus 1 by TB. What about this edge? So minus F2 plus 1 by TB. So it is basically like F1 minus F2 into 2 times RB. You will get this one. So if you see earlier, the bandwidth was just 2 RB, but to that 2 RB you have some extra component. So FSK needed higher bandwidth. All right. So clear in terms of advantages, disadvantages, how you need to think from FSK, PSK, all these modulation schemes. Clear? But still, the communication engineer is not happy here because he didn't get what he can implement in the practical system, right? The thing is that, see, the thing is that, okay, we had considered 10110, right? So, uh, so 10110. Now I was telling, for one we will use frequency f1, for 0 I will use frequency f2, right? Now it became more challenging, like how to design this f1 and f2. See, let's say I will design this f1 something like this. Okay, then I will design f2 frequency such a way that, okay, not correct, I mean, this is high frequency, right? So this is low frequency. Let's say I just design like this. Now what is happening, can you see here, like still we are getting this phase discontinuity. Still we are facing that problem. First of all, this probability of error is low compared to PSK, and whatever PSK we had, the same phase discontinuity is there. Okay, second point. The third one is the bandwidth is also higher in case of FSK, but here in PSK it was less, right? The problem is not solved. So intelligent design of these two things should happen. So that is like, what is the constraint? I mean, if you clearly see it, so you have to take this frequency f1 and f2, that should be integral multiple of your tb. Okay, this is one tb duration, right? Or you can say 1 by rb. It should be integral multiple of which means that whatever frequency f1 you take, so it should completely fit there. Is it fitting here? How many cycles? 1.5 cycles, right? Correct. What about here? This is fitting one exact 1 cycle. So like that you have to choose. Maybe this is high frequency, right? I will say, I will fit 3 cycles here. Maybe here I will fit 2 cycles. If you are doing like this, then you will see that there is no phase discontinuity. Phase continuity will be maintained. So F1 and F2 choice will actually remove this phase discontinuity problem here. Okay, then what are we left out? We have bandwidth problem. So what is this modulation scheme called? If you are choosing that way, so they said it's a new modulation scheme. I will call it as continuous phase FSK. Got it? So now bandwidth is a problem. Okay. So now again, what they have done, like to reduce the bandwidth, the design of F1 and F2 is chosen such a way that, so let's say I will say delta F is equal to F1 minus F2. The difference between these two should be as low as possible. So if we can bring in such a kind of design, that is possible, and that was also proposed. So maybe this is having the bandwidth just 1.5 times of PSK bandwidth. Okay, let's say this is FSK bandwidth. So this deviation also, it was brought down. The F1 and F2 was chosen in that way, and they called it as another modulation scheme, that is called as minimum shift keying. Got it? So in the minimum shift keying, as the name itself says, frequency wise there is almost no phase discontinuity, and also the deviation between the frequencies is as low as possible, so that the bandwidth is not very large. Okay, so then actually in case of MSK, right, the modulation scheme is used. I am not going through the details of those modulation scheme, but I want to talk about the constellation points. Okay, so the constellation points, again, MSK is a special case of FSK, right? Because from FSK only we have developed FSK, and even CP FSK. So how does my constellation look like? This MSK, what does it do? The way it is designed, right? It takes 2 bits in one shot, and we are going to transmit the symbol. By that way, we will anyway have two basis function, phi 1 of t and phi 2 of t. So this is one constellation point. We are taking 2 bits, right? So then if you are taking 2 bits, what are the combinations? We can have 0, 0, 0, 1, 1, 0, 1, 1. So if you are representing in terms of our basis function, then it's basically square root of EB, and this is also square root of EB. But maybe for minus, sorry, for 1 it will be minus square root of EB. So basically we will have these four constellation points. Okay, so now in order to calculate the probability of error, we need to take this distance. So I mean, if we take this distance, and what it is, what it is coming out is, it is similar to that of the QPSK, which we will look into this now. Okay, so basically, I mean, at the end of the day, what happened is, uh, we try to eliminate the disadvantage one by one, and even with respect to probability of error also, we brought down to a significant level, and it was made equivalent to QPSK system, and phase discontinuity is not there, and bandwidth also, it is not taking too much bandwidth. So this became actually uh, practically implementable. But there is one disadvantage with this. In case of minimum shift keying, or in terms of phase shift keying, the problem is that um, the transmitter or receiver design is very complex. Okay, so for that reason, it did not survive for a long period of time. You're getting the point, right? So then what does it mean? Like I said, it becomes practically, it was implemented practically. So basically it was implemented in our, so right now we are in which generation? Okay, so please tell, in right now we are in which generation in case of your mobile technology? Yeah, right now, okay, what you're using is 4G, right? 4G communications, but 5G is going on. The developments and many other deployments are going on with respect to 5G. So in case of 2G, old generation 2G, so the technique which was used is this MSK only, minimum shift keying. Okay, so they call it as actually GMSK. They've used Gaussian as a pulse shaping filter, right? We had used the rectangular pulse, but there it was used Gaussian. We'll see if time permits. I'll come to that. But this was used in case of 2G. You got the application right, but from 2G we wanted to have much more higher data rates, much more services. So it did not survive for long. It did. So then we had to move to 3G. So till now, whatever I have spoken is, I mean, what do you say? Like it's a binary modulation schemes, because I considered only bit one and zero, right? Only in case of uh, MSK, I was telling that we considered 2 bits in one shot. So similarly, in case of PSK, okay, can we consider 2 bits in one shot and perform? So let us see the constellation points. When we had considered only um, one bit, right? So basically we are going to alter the phase. So how much maximum phase we have? We have 360-degree. So out of this 360-degree, we used 0 and 180-degree. right? There was only two combinations, two bits. But the moment we are going to pack the bits, let's say I will take two bits in one shot, then 00 01 10 11. Yeah, how would you like to divide this? Yeah, go ahead and tell, how will you divide? That's 360 by 4, right? So 1990. So basically, these points, I mean, if you do that mathematical calculations, let's say 45 degree, I will say for first one, I will transmit with 45 degree. So this is the point. Okay, let me. Okay, this is the point. For next, I will transmit 135 degree. So this is the point. Then similarly, this is another point. This is another point. We have 4 points. Okay. So we are now we are saying this is 00 01 10 11. Now basically now we again we have what we have to do. We have to get this distance, right? So we need a probability of error. So basically we need this particular distance. Okay. So in case of PSK, what is the advantage? PSK, when we are taking it as 2 bits, it is called as quadrature phase shift keying, QPSK. So here the main advantage is that using the same bandwidth, okay, at a time you are going to transmit to 2 bits, right? So you are having more data. See, earlier in 2G, what was the problem you had? Maybe you guys were not using, but like, but you can guess the problem, right? In case of 2G, even to an extent in case of 3G, what was the problem? Like the moment you open some video, then video used to buffer a lot, right? So it will open for a short duration, then it will buffer a lot. But nowadays, what do you guys want? Much faster, everything live, right? You want to watch IPL live without any buffer, correct? So we have that bigger expectations or much bigger demand, so that we want to proceed for different modulation schemes. That's where we are trying to pack more and more bits into this uh, into same bandwidth. So that's where we had gone for much more modulation schemes. So here now it is QPSK. Okay. So from here even 8 PSK is also proposed, and in the 8 PSK what we can do, like 3 bits, right? So again you're dividing this entire into 8. So maybe 1 2, so you will divide totally into 8, right? So now you have 3 bits at a time you are going to take, which means you have got 8 combinations. So at a time you are going to transmit 3 bits. So in the same bandwidth, in the same duration, you are trying to pump in more and more bits, which means that more and more information. That's why you will have better download speeds or better uploading speed. But 8 PSK again it had got some problems, so they defined some different variations of 8 PSK. So they identified that and they call it as 3 pi by 8 uh, 8 PSK. Okay, so this was used in 3G. It was used in 3G. There we used to call it as edge technology. Okay. Now what happened, we are not satisfied with the data rate, we want more data rate. So one of the modulation schemes proposed is, yeah, why can't I club the modulation schemes and bring in some new modulation scheme, that is amplitude is there, then you have phase, you club both of them and say quadrature amplitude modulation scheme. Okay. This is like a hybrid one. I think even in analog communication also there was something like hybrid. I think remember. So here, what are you gonna do? In the earlier case, you are only focusing on the you are only focusing on the um, uh, phase. But if you see the amplitude, always it was one. Okay. Now in this case, higher modulation schemes are proposed, which is called as 16 QAM, or you can even say 64 QAM. So how does my constellation look like? Let's say I will take the 16 QAM. It looks like this. Okay. So see, when it was in the year, it was all, I mean, all the constellation points were lying on the unity circle. Okay. But here if you see, the outer one is lying on the unity circle, whereas these are not exactly having the amplitude unity. So what I mean to say is, here basically you are, when you take this particular scheme, right, or let's say this particular point, you are going to modulate both the amplitude and as well as the phase of the carrier. Okay. So basically, let's say this is in the complex domain. I will take this is a real part, this is imaginary part. Then any point, how can we write a plus jb, right? So in the beginning I was referring to this only, like we will get some complex quantity. So this a plus jb, we can write r e to the power of j5, correct? So in case of just psk, this r was always 1, we are changing only phase. But in here, in case of QAM, this r is also not equal to 1, it can be any other value, and also you will have a phase variations. Okay. So by that way, in 16 QAM, how many bits we are able to transmit at a time? 4 bits. Then 64 QAM, 6 bits, right? So in right now today, whatever you are using in your mobile phones, like we are using this form, and we are using 16 com, 64 com, even we have up to 256 com. Okay, where we transmit 8 bits in one shot. But in the future, like let's say Wi-Fi. Okay. So you might be using your college Wi-Fi or Wi-Fi, right? There even they are a little bit advanced, and they are using 1024 QAM, where they're going to transmit 10 bits in one shot. That's why you will say, hey, switch to Wi-Fi. Hey, here I'm not getting the much faster data rate. Can I download it faster? Switch to your Wi-Fi, then it is much faster, right? Because they're going to use higher modulation schemes. Okay. So there are many other modulation schemes like differential phase shift keying. I will not go through that. It was also not successful. Okay. Now we will actually come to, yeah, now we will actually come to detection part. Okay. So I will just touch upon the basic concepts of detection and estimation theory. See, first and foremost thing in case of mm, detection part is, you need to understand the noise, right? Because there is a topic under the presence of noise, how are you going to detect your signal, or how are you going to estimate it? Because in the receiver also, the moment you have lots of hardware, you will see that there is a significant noise, right? So we need to model that noise in a better way, so that it is easy for us to analyze, and it is easy for us to come up with the algorithms or estimators or detectors, so that we can recover back our message signal. Okay, before I continue with this, let's say estimation or detection theory, you have any questions with modulation schemes? Anything else you want to know there? Okay, so I will get to the point. One of the detection scheme is that when you transmit a signal, okay, then under the presence of noise, how are you going to estimate it? So for that, first thing what you need is to know the distribution of that noise. Okay, so the basic concept again is the Gaussian distribution. So in the Gaussian distribution, this is how the PDF would look like, and if you are asked to write the PDF equation, and this is what you should be writing it. Okay, so we say the mean of this is 0 and variance is sigma square. Particularly, I mean, what does that mean? Which means that let's say you have you have a number 10. Let's say for example 10. You want to transmit 10. Let's say noise could be 0.001. So this around this 10, your samples can vary. It could be 9.99, something like that, right? This variation depends on your variance of your noise. Okay, if variance is too much, you transmitted 10 but you are getting some 2 or something like that, variation, that is variation is too much, right? So if you're getting variations of this much, it is okay. I mean, we will be in a position to recover better. So one more point is that is one random variable which we had considered. Let's say we have many random variables like that. Let's say n random variables, and each of them are mean 0 and variance sigma square. So the assumptions which we will go is they are all IID, which means they are all independent and identical random variables. So in that case, if each of the PDF of noise is given by this equation, okay, then how can I write the joint PDF of those n samples? So joint PDF would be just the multiplication of individual PDFs. Okay, so these are all like basic important concepts. Even in gate examinations, it might be asked. I'm just trying to build the basics like before even we get into one of the detection concept. Okay, okay. Now we will get into the detection concept. Now what I will do. So this theta, okay, theta is constant. Like I was just now telling some value 10, right? So let's say theta is that constant value, but this w high is your noise of variance 0 and sorry, variance sigma square and mean 0. Okay, so theta, let's say I have transmitted theta, but at the receiver I have got theta plus w1 because of noise. So what can we tell about these n samples? All these n samples are noisy observations, right? Now how can I write about the joint PDF? So this W1 we already saw how to write the equation. Now what we need to understand here is if W1 is Gaussian, what can we tell about X1? That is also random quantity, correct? Because this was constant actually, but this randomness came because of this w1. So that's why whatever the observations, whatever we are receiving, that is also random in nature, and that will also have we need to calculate what is the mean. Okay, mean will be this theta, right? Because mean of this is 0 anyway. What about variance? Constant value variance is 0, but variance of w1 is there, so variance is sigma square. So to this one, if you are going to write the equation, actually individual PDF, we can write it like this, or or we had written like this, 1 by square root of 2 pi sigma square e to the power of minus w1 square by 2 sigma square. So this is the equation. Okay, this we need to remember it. See, this w1 you substitute. In other words, what I would say is w1 is equal to your x1 minus theta, correct? So that exactly substituted here, and we got individual. But for n number of samples, this is exponent, right? So in the exponent part, it will become summation. So I will get it like this. Okay, this equation is there, but in an intuitive way, how you can estimate? Let's say you have noise, right? So you have got. I was telling you have transmitted 10, but you are getting 10.0111, and let's say you are getting 9.9, something like that. So you have got some many observations. So how do you try to recover your signal? Like what simple strategy you can apply? Just think, what can you apply? One is just take average, right? So let me write that over here. Okay, let's say this is 10. Okay, this is the line where I will get 10. So over a period of time, this is let's say time. Over a period of time, I am getting samples like this, around this 10, right? So best thing is, if you take the average, maybe you might get 9.999, something like that. You close to what you transmitted actually. But I'm trying to say with mathematical equations, how exactly we can try to actually estimate that with equations. So the thing is, now we got this joint PDF, right? This joint PDF, whatever we got, so this is nothing but your actually likelihood function. Okay, so this is the likelihood function. But once we have the likelihood function, what is the question we have? What is the value of theta, which best explains all these samples, which means that using these samples, how best what strategy should I apply in order to get my theta in a best way. So for that, we already saw the likelihood function, right? So that likelihood function, you need to maximize the likelihood function. So basically, this is the joint PDF. You need to maximize this joint PDF. So if we want to maximize this, as per equation, this is negative, right? E to the power of something in the negative. So this particular quantity you need to minimize. So I will actually get this one. How to find the minimize, right? Mathematics, right? Again. So if you want to minimize this, differentiate with respect to that particular parameter and equate to 0. So if you differentiate, finally what you will get? You will get this equation. This is the estimate. This is your estimator equation. So it says that whatever our intuitive way we thought, right? So it is also giving the same thing, that okay, if you have many noisy samples and if you want to estimate that constant quantity, then you have to take the average of all your observations. Okay, is it clear? So is it clear? This is this is telling you take average. This is the estimator that it is giving to us. Okay, so but now let us try to see this one, theta, right? We will try to analyze some important observations here, that this theta at, this is estimate, right? This theta at should be very close to theta whatever you transmitted. That should be the goal, which means that this variation, okay, variation should be as low as possible. So for that reason we will try to see the variance of this, how to calculate the variance of this, because xi we saw that is also random quantity. We saw the variance of this xi. What was the variance? It was sigma square, right? So if you calculate the variance of this, I will not go through the equations, but it is calculated, okay, variance of the estimator. So if you apply the expectation formula, even I think in analog communication you have learnt about the probability and detections, probability theory, right? So probability theory is very much important, or it is a prerequisite for this particular estimation or detection theory. So you apply this expectation, and then you get the variance. Okay, variance of the estimator comes to be sigma square by n. All right. Now is the important observation. What does it say? So if this sigma square sigma square is large, okay, then then even your estimator theta at whatever variance you got, that is also large. So that's why I was telling you transmitted 10, but your variation is too much. So let's say you're getting only 2, or you, let's say you're getting 20, like that. Your variation is too much. Then your estimate is also not good. But let's say your estimate, you want your estimate to be good in such case, then what can you tell? Hey, right now whatever samples you have given to me, the variation is too large. I would like to see more samples, right? So that is when, let's say you will request for 100 samples, or let's say you request for 1000 samples. More the number of samples, you will see that based on this equation. Okay, if n is large, then overall this variance comes down, which means that your theta at, which is the estimate, is becoming very close to your theta. Okay, got the concept? So more the observations, you can take better decisions, right? So that's what it is coming to. Any questions till here? Any questions? See, I will go to one more concept which is widely a problematic in case of communication system. That is timing offset. Okay. See, let's say you transmitted signal at t, this point t is equal to 0. Okay. By the time it reaches to the receiver, it is taken some amount of time, and it reached at t0. Okay. So we need to correct it, right? Otherwise we will not get at, let's say you transmitted at this point, and at the receiver also you are looking at the same point, then actually there is no signal. Signal is somewhere else. So we need to correct it. What is the way to correct that one? So let's say we know this signal, let's say s of t already we know. So S of t, you take it. I mean, let's say this is the received. For example, let's say this is your received. I will say R of t. At so this is transmitted. now at the receiver, what you do, you take the same signal S of t and you try to shift it. Let's say for first time, this t naught is, let's say, 10 for example. Okay, first time you try to shift it by 2, so t minus 2, then you try to multiply it with r of t. R of t is whatever you transmitted, which is S of t, right? So in that case, let's say this is t naught. You also place the same signal somewhere here, and you're trying to multiply both of them. Both of them are not overlapping each other, right? There is no overlap basically, so it will give almost zero, nothing. It will not give anything. But let's say there is a partial overlap. Okay, so let's say there is a partial overlap, then you will get something. Okay, let's say I will say for now a1, but only when these two are exactly overlap, then you will get the maximum area overlap, right? So that's when you will get, let's say, maximum signal, I will say a max. So that's how, that is also one of the ways. I mean, I just told it in a intuitive way, but with mathematics also it will come to the same conclusion. Okay, what do? You take the signal, the same signal, you try to slide it wherever there is a maximum. Okay, that is when is your timing delay estimated correctly. Okay, so whenever you get a max for whatever the value, let's say in this case t naught is equal to 10, you will get. And now you know that actually your signal has been shifted by 10 samples, or duration of 10. Then I will directly go there and look, or you correct it. It is shifted by 10, you shift it back, right? And then you start processing your information. So that is one concept. So last one I want to talk about, actually I was telling, right, this maximization. So it will come to what is known as correlator. So similar to this, I want to touch upon one last concept. Yeah, okay. So we have seen ASK, FSK. We spoke about the transmitter part, right? Let us quickly look into the receiver part. Okay. So what are we doing? So we finally, at the end, we considered QAM, right? A hybrid one, which is changing both phase and amplitude. So I have taken the same equation. So this is what I have transmitted, and then that is added with the noise, and that is this is received at receiver. So amplitude and phase are unknown quantity. That is what we need to estimate or detect at the receiver side. So how can we do that? So basically, um, you apply the mathematics cos a plus b. So I will get cos a cos b minus sin a sin b. Then if I separate it out, I would get something like this. Okay, I would get cos, this is one basis function, or this is one carrier. Okay, this sin is another carrier. So theta 1 and theta 2 are unknown quantities. Okay, theta 1 a cos phi, theta 2 minus a sin phi. So whatever the amplitude which I transmitted, or whatever the phase which I transmitted, that is embedded, that information is embedded here. Okay, now what I will do, you just take all the n observations. Okay, you take all the n observations and you try to write it in a vector form. Okay, so now I will not try to go through the mathematics, but when such a form is there, this is x bar. Okay, this is matrix H, and this is theta bar. Okay, vector again, this is W bar. So basically I have x bar is equal to h theta bar plus W bar. All right. So for this, the estimator is already, you know, we can prove the estimators. One of the estimators is the least squares estimator. So if we try to actually, if we try to actually apply that, finally we will get the correlator. I just want to show that. Yeah. So if we try to apply that, I will just try to apply that estim estimator. So this is least squares estimators. Okay. So I know what is my h. I will take it. These are x bar is my observations or received signal. So I will perform h transpose into h. Okay. If I perform this, then finally I will get. I will not go to the mathematics, but I will get something like n by 2 into identity. Okay. Then I have H transpose into X bar. So this is anyway identity, right? This two if I multiply, then finally I will get my theta 1 to be like this and theta 2 estimate to be like this. So these are all nothing but your correlators. Okay. To the received signal x of n, you are going to correlate with cos omega ct. So this is exactly what we were doing, right, in even in another communication or in your uh, even in our ASK we were doing something like that, right? So let's say just simplistic one, ASK. Okay, let us see the detection problem here. So how did we transmit? Plus 1 AC cos omega ct, right? 0, we didn't transmit anything, right? Now can you tell me, if this is transmitted, what should I do at the receiver? So this is AC cos omega ct I transmitted. Okay, so over the channel. Now I have the receiver here. From here onwards, receiver. In the receiver, we were asked or we were directly doing cos omega ct multiplication, right? So that, so this is like, okay, let's say this for now the noise is 0. Then at this point I have this x of t which is equal to AC cos omega ct. This is my received signal, right? To the received signal I am just multiplying with cos omega ct. Am I right? So that is exactly, even these equations are going to tell you by using the least square estimator, that here I had considered n samples. Let's say I will consider n is equal to just 1. Then how does it become? N is equal to 1. This boils down to just 2 into x of n cos omega ct. Let us use this one only. Okay. So I will use 2 times cos omega ct and x of t. This is at here x of t, right? So here 2 into x of t cos omega ct. I've used the same correlator here. So if I perform this, what do I get? X of t anyway we know, that is AC cos omega ct. To this I am going to multiply cos omega ct. So cos into cos, cos square, that will give 1 plus cos 2 omega ct by 2, right? So then I have 2 AC. So 2 to get cancel. Then what would I get? AC plus AC into cos 2 omega ct. This is a high frequency component. Where is my message embedded? My message is in here, correct? What I have transmitted is AC. AC we saw the relation with the square root of EB, energy of the bit, right? So I need this one, but this is a unwanted quantity. I will use after this low pass filter. So low pass filter will filter out only this. this will be eliminated, and I got back my message. You got this correlator? So we saw one constant value estimation with the noisy observations. That is one thing. Second thing, what we have seen is the estimate of the timing delay. Okay, that also we saw in an intuitive way. Third one is the correlator which we are using in our communication system to do the up conversion, down conversion. Okay, so any questions you have? So no questions, completely understood. So no questions, two possibilities, right? Plus one, you understood everything. Zero, you didn't understand it. Okay, that's all I had for today. So what I would say is, yeah, you can contact me for any questions. I can answer if you have any specific doubts. Okay, so I mean many of the concepts which I'm trying to cover in my YouTube channel as well. So this is a YouTube channel which you can go through. I will be covering related to placements, something related to IS studies. Okay, even this I have tried to capture the video, so even I will upload the video in this particular channel. All right. Yeah, thank you very much.